Hi, welcome to this video on special relativistic time dilation. So there are a bunch of well-known but confusing effects in special relativity. There's length contraction, time dilation, and the twin paradox. Here, we're going to be talking about the second of these, time dilation. So let's say we have two spaceships, ships A and B. Now each ship is in its own inertial frame. So what does this mean? Well, let's say that some object on either ship is not fastened down and is free to move, subject to no forces. If the ship is in an inertial frame, that object will not accelerate relative to the ship. It will remain at rest or at constant velocity. So for example, a spaceship moving at constant velocity is in an inertial frame, but one that is firing its engines to accelerate is not. If a ship is in an inertial frame, to the crew of that ship, the state of the ship is indistinguishable from being at rest. Okay. So either ship can consider itself to be at rest, but the ships are moving relative to each other. We can look at this situation from the inertial frame in which ship A is at rest. This is called the rest frame of ship A. Now let's say in the rest frame of ship A, ship B has a velocity v, which is pointing to the right. Alternatively, we can look at this same situation in the rest frame of ship B. In this frame, ship B at the bottom is at rest, while ship A has a velocity of minus v, which means it's moving to the left. Okay, so now let's say each ship carries a clock set to that ship's time. The clocks are positioned such that they can be read by the other ship. So ship A's clock shows ship A's time, and ship B shows ship B's time. If either ship compares the rate at which their own clock is ticking with the rate they observe from the clock on the other ship, they will conclude that the other ship's clock is running more slowly than their own. So ship A will conclude that ship B's clock is running slow, and ship B will conclude that ship A's clock is running slow. So each ship says that the other ship's clock is slower than their own. And note here that we mean slower, not behind. They measure the rate of the ticking of the clock on the other ship and conclude that it is ticking more slowly than their own clock is. Now, this might seem like a contradiction. After all, how can ship A's clock be running more slowly than ship B's clock, while ship B's clock is also running more slowly than ship A's clock? Okay, so here are the points we want to make in this video. When ship A compares its clock to that on ship B, and when ship B compares its clock to that on ship A, they are actually doing subtly different measurements. We'll show how those measurements are different and how there is no contradiction. We'll also see that by altering its measurement, either ship can observe either direction of the effect. Okay, so let's talk about what background info you need for this video. This video is ideally made for someone who has had exposure to the idea of time dilation, but who wasn't comfortable with it. Otherwise, it will be helpful if you've had some exposure to special relativity and have seen the Lorentz transformations, but we will try to make the video roughly comprehensible even if you haven't seen those things. Okay, so first we should talk about something called the relativity of simultaneity. It's critical for understanding time dilation, length contraction, and the twin paradox. Okay, so what is the relativity of simultaneity? It's basically the following. Events which are simultaneous in one inertial frame are not necessarily simultaneous in another. Okay, so to get started, we need to mention the two axioms of special relativity. The first is that the laws of physics are the same in all inertial frames. And the second, which will be especially important, is that the speed of light is the same in all inertial frames, a constant that we call c. We will apply these axioms in two inertial frames. One, a spaceship, and two, a spaceport that the spaceship is flying by. We will see that events which are simultaneous in the spaceship rest frame are not necessarily simultaneous in the rest frame of the spaceport. Okay, so let's say we have a rather long spaceship. It is at rest in an inertial frame. In the middle of the spaceship is a flashbulb. On each end of the spaceship is a light sensor. The light sensors are each a distance d from the flashbulb. Okay, so let's work in the spaceship rest frame. The flashbulb briefly illuminates. The light front from the flash travels out from the bulb in all directions at speed c. After a time d divided by c in the spaceship rest frame, the light front reaches both sensors, and they register the flash. The left and right sensors' registering of the flash are simultaneous events in the spaceship rest frame. Okay, now we will look at the exact same physical situation, but with the spaceship flying by a spaceport. Here, the spaceport is shown as a gray slab. It is also at rest in an inertial frame. We're going to look at the same situation as before, but this time in the spaceport rest frame. So here, the spaceport is at rest. But in this frame, the spaceship is moving at velocity v, to the right. Okay, so the flashbulb illuminates. Now the speed of light is c in all inertial frames. So in the spaceport rest frame, the light front also moves out from the location of the flash at speed c in all directions. Meanwhile, though, the ship is also moving to the right. The left sensor is moving toward the light flash, while the right sensor is moving away from it. The left sensor registers the light flash. The light front continues moving out from the location of the initial flash. The light front will catch up with the right sensor eventually, and the right sensor will register the flash. Okay, so now we've looked at this same situation in two different inertial frames. In the rest frame of the spaceship, the two light sensors register the light from the flashbulb simultaneously. In the rest frame of the spaceport, they happen at different times. So whether or not two events are simultaneous can depend on what frame you're in. Or, in other words, simultaneity is relative. We'll come back to the relativity of simultaneity after we discuss the Lorentz transformations. Okay, so let's talk about those. Let's say we have two inertial frames. Some event occurs at a certain time and place, as determined in one of the frames. The Lorentz transformations are a set of equations that allow us to determine the coordinates of that event in the other frame. We're not going to derive the Lorentz transformation equations here, but instead just discuss what they do. They can be derived from requiring that the speed of light be the constant c in both frames. Okay, let's return to our situation of a spaceship flying past a spaceport. We will work in the spaceport rest frame. The spaceship is moving to the right with velocity v. An event, like two rocks colliding, occurs at some space-time point. Observers stationed on the spaceport and the crew of the spaceship would like to describe when and where this event occurs. Let's see how observers stationed on the spaceport would define a coordinate system. Observers stationed on the spaceport define a set of coordinate axes with coordinates x, y, and z. The x-axis is aligned with the direction the spaceship will be traveling. They put the origin of the coordinate axes, so the point where x, y, and z equals 0, in the center of the spaceport. They also have a clock. They will use this clock to measure the time coordinate t. Both the coordinate axes and the clock are at rest in the spaceport frame. So, the observers stationed on the spaceport would describe the time and location of the event with the coordinates x, y, z, and t. Okay, now let's look at how the spaceship crew would define their coordinate system. This is defined in the spaceship rest frame, where the spaceship is not moving. The spaceship crew defines coordinates called x prime, y prime, and z prime. The origin of this set of coordinates is in the middle of the spaceship. The crew of the spaceship also has a clock, which they use to measure their time coordinate t prime. Both the axes and the clock are at rest in the spaceship frame. The spaceship crew would describe the time and location of the event by specifying the coordinates x prime, y prime, z prime, and t prime. So, in the spaceport rest frame, the event occurs at x, y, z, and t. In the spaceship rest frame, the event occurs at x prime, y prime, z prime, and t prime. The Lorentz transformations give the conversion from one set of coordinates to the other. Okay, so let's go back to the spaceport rest frame. The spaceship will fly by with velocity v. The axes of the spaceship coordinate system move with the spaceship. Both the spaceship crew and the observers stationed on the spaceport need to decide how to define the zero of their time coordinate. They decide that the space-time point where the origins of the two sets of axes coincide will define the zero of their time coordinates. So the space-time point where this overlap happens is at t equals 0 and at t prime equals 0. Okay, so to recap, the observers stationed on the spaceport define the origin of their coordinate system to be the center of the spaceport. The spaceship crew define the origin of their coordinate system to be the center of the spaceship. When the center of the spaceship and center of the spaceport coincide, the space-time point of that overlap is defined to be at t equals 0 and t prime equals 0. Okay, so here are the Lorentz transformation equations. We will mostly be interested in the equations relating x and t to x prime and t prime. We'll be especially interested in the equation for t prime. The equations relating y and z to y prime and z prime won't come up here. Now, you shouldn't be worried if you don't understand these equations the first time you see them. They are far from obvious. The requirement that the speed of light takes the same constant value in both frames makes these relations highly non-intuitive. Okay, so let's discuss the relativity of simultaneity again. Let's take another look at our spaceship. For the moment, we'll work in the spaceship rest frame. We're going to put 3 clocks on the spaceship, one in the center and one at each end. The distances between the 2 end clocks and the middle clock are the same. These clocks can be synchronized in the rest frame of the spaceship via a light signal sent out from the middle clock. The spaceship crew know the distance from the middle of the spaceship to the end clocks and can use the light signal to set all 3 clocks to the same time t prime. Meanwhile, back on the spaceport manager sits in the middle of the spaceport, which was defined to be x equals 0. 2 other observers are also positioned on the spaceport. There is a front observer and a back observer. All 3 spaceport observers are positioned so that they can observe the spaceship clocks at t equals 0. The front observer is at x equals plus L, and the back observer is at x equals minus L. The front, middle, and back observers are close enough to their respective spaceship clocks at t equals 0 to observe them with negligible time delay from light going from the clock to their eyes. Now, each spaceport observer also gets a clock. These are synchronized in the spaceport frame via a light signal. Now, the spaceship will fly past the spaceport. As we said before, the middle of the spaceship will pass the middle of the spaceport at t equals 0 and t prime equals 0. At t equals 0, the 3 spaceport observers will record the times they see on the spaceship clocks directly in front of them. So, what spaceship times t prime will they record? We've already said that when the spaceship is in the middle of the spaceport platform, the time at the origin of both coordinate systems is defined to be 0. So we already know that the spaceport manager in the middle of the platform will see t prime equals 0 on the clock directly in front of them. To get the times on the other two clocks, we'll use the Lorentz transformation equations. Specifically, we'll use the equation for t prime. Okay, so here's that equation. T prime is the ship time. All of the measurements are being made at t equals 0, so we can set that to 0 in the equation. But we see that t prime depends on x. This means that t prime depends on where the clock is. Okay, let's take that equation and get the values for each of the two remaining spaceship clocks. Both observations are made at t equals 0. The back clock was at x equals minus L. Substituting t equals 0 and x equals minus L gives us the value of t prime for the back clock. So t prime equals VL over c squared divided by the square root of 1 minus v squared over c squared. For the front clock, we substitute in t equals 0, x equals plus L, and get a result of the same magnitude and opposite sign. Okay, so here are those results. The times on the spaceship clocks are not the same. The middle clock shows t prime equals 0. The rear clock shows a later time, and the front clock shows an earlier time. Smaller x implies a later t prime, and larger x gives an earlier t prime. So the relativity of simultaneity strikes again. In the spaceship frame, all three clocks show t prime equals 0 at the same time. In the spaceport frame, they do not. This will be central to understanding time dilation and how observers in two frames can each think the other's clock is running slow. Okay, so we're finally ready to talk about time dilation. If you have two observers, each in their respective inertial rest frames, moving relative to each other, they will each think that the other's clock is running slow. Let's see how this comes about. Let's go back once again to our spaceship. Here, let's look at it in its rest frame. This time, let's cover it with clocks. These clocks will be synchronized in the spaceship rest frame. Meanwhile, the spaceport manager sits in the middle of the spaceport at x equals 0. The spaceship, covered in clocks, will fly by. The spaceport manager will look at each clock as it passes by. So, first they look at the first clock, then the second, then the third, and so on. What times does the spaceport manager see on the series of clocks passing by at x equals 0? Again, we'll look at our Lorentz transformation equation for t prime. Again, t prime is the spaceship's time. This time, all of the measurements are made at x equals 0. So we substitute x equals 0 into this equation for t prime and get that t prime, evaluated at x equals 0, is equal to t divided by the square root of 1 minus v squared over c squared. Okay, so here's the same relation that we just derived. For a massive object like a spaceship, the magnitude of v is always less than c. This means that v squared is less than c squared, and that means that the square root in our expression is less than 1. This means that t prime, evaluated at x equals 0 is t times a number that is greater than 1. And this means that t prime evaluated at x equals 0 is evolving faster than t. The series of clocks passing by at x equals 0 shows t prime evolving faster than t. For a concrete example, let's go back to the 3 clock case. At t equals 0, the spaceport manager sees the middle clock with t prime equal to 0. At t equals L over v, the spaceship has moved a distance L. The rear clock shows L over v divided by the square root of 1 minus v squared over c squared. This is greater than t, which is L over v. Okay, so that's what happens if the spaceport manager at x equals 0 looks at the series of clocks passing directly in front of them. The series of clocks shows times evolving faster than the spaceport clock. Isn't this the opposite of what we thought we'd see? And the answer is no, but we have a bit more work to do in order to see this. So now let's ask a different question. What happens if the spaceport observers instead watch a single clock on the spaceship as it travels by? So we'll look at how the time shown on the middle spaceship clock evolves as the time in the spaceport frame goes from t equals 0 to t equals L over v, which is when the spaceship has moved a distance L, as seen in the spaceport frame. But first, we should ask, how would this measurement be made by the observers stationed on the spaceport? At t equals 0, the observer at x equals 0, in the middle of the spaceport, would read the time t prime, which we've previously said is 0, on the middle spaceship clock. At time t equals L over v, the rightmost spaceport observer would look at the middle spaceship clock and record its time t prime. Then the two spaceport observers compare observations to determine how fast the middle spaceship clock was ticking. Alternatively, we could forego the additional spaceport observers if the middle spaceport observer had a telescope with which to read the middle spaceship clock when it reaches x equals L. But then that observer would need to take into account the time delay for light to go from the clock at x equals L to their eye. It's simpler to think of the rightmost spaceport observer making the second observation of the middle spaceship clock. So we'll do that. Okay, so let's get to the actual calculation. We can look at this as the sum of the two effects we saw already. First, we saw that the series of clocks passing by in front of the spaceport manager at x equals 0 showed times t prime evolving faster than t on the spaceport manager's clock. Second, we saw that at a given time t, the clocks on the spaceship are not synchronized. Those at smaller values of x show later times t prime than those at larger values of x. This latter effect is important because a clock on the spaceship is moving from smaller values of x to larger values of x. Okay, so let's look at the results that we already have and see how we can put them together to see how t prime evolves on the middle clock as it moves to the right. At t equals 0, the spaceport manager at x equals 0 sees t prime on the middle spaceship clock. We want to know how t prime changes on the middle clock as it moves to x equals L. At t equals L over v, the ship has moved a distance L. The middle clock is now at x equals L. We saw before that at t equals L over v, the rear clock is located at x equals 0 and shows a time t prime of L over v divided by the square root of 1 minus v squared over c squared. Let's see how we can get the time on the middle clock using this previous result. We also saw before that in the spaceport rest frame, the clocks on the spaceship do not all show the same time. We can look at the difference in times shown on a spaceship clock at x equals 0 and one at x equals L. We previously evaluated this difference at t equals 0, but it will also hold at other values of t, like we're interested in here. The difference in time shown on these spaceship clocks in the spaceport rest frame is minus VL over c squared divided by the square root of 1 minus v squared over c squared. Let's apply this difference to get the result we're looking for. Okay, so let's figure out the time on the middle spaceship clock at t equals L over v. We previously got the time on the rear clock at t equals L over v, so now we can just apply the offset that we just saw. This gives us the expression for t prime on the middle clock shown at right. Okay, let's simplify that expression down. We have two terms. Each contains a square root in the denominator. We can pull that factor out front. We can also pull out a factor of L over v. If we do that, we get the middle expression, which contains a factor of 1 minus v squared over c squared. That is partially canceled by the denominator, and we get L over v times the square root of 1 minus v squared over c squared. Okay, so the expression that we had before is now much simpler. We see that the time t prime shown on the middle clock is equal to t, which is L over v, times a factor that is less than 1. This means that the middle clock is running slow as viewed from the spaceport frame. Okay, so let's recap. If someone on the spaceport watches the clocks on the spaceship as they pass directly in front of them, the times on the series of clocks on the spaceship appear to be running faster than their own spaceport clock by a factor of 1 over the square root of 1 minus v squared over c squared. If someone on the spaceport watches a specific clock on the spaceship, that clock will be running slower than their own by a factor of the square root of 1 minus v squared over c squared. This latter effect is how time dilation is usually described. Moving clocks run slow. Okay, but now what happens if someone on the spaceship tries to observe the spaceport manager's clock? Actually, we have already solved this. Let's take a look at how people on the spaceship would measure the rate of the ticking of the spaceport manager's clock. The middle spaceship clock and the spaceport manager's clock were aligned at t equals t prime equals 0. Later, the rear spaceship clock is aligned with the spaceport manager's clock. The spaceship crew can compare the spaceport manager's clock to their own middle and rear clock at these two spacetime points. But this is the same comparison as what was done when the spaceport manager compared their clock with the series of spaceship clocks passing directly in front of them. We already saw what happens when comparing the spaceport manager's clock to the rear spaceship clock. The time t on the spaceport manager's clock is smaller by a factor of the square root of 1 minus v squared over c squared. So the spaceport manager's clock is slower by a factor of the square root of 1 minus v squared over c squared. So, when the spaceport manager watched the series of spaceship clocks passing directly in front of their chair, they were actually observing time dilation of their own clock from the perspective of the spaceship. Thus, they saw their own clock running slow compared to the series of spaceship clocks. The spaceport observers saw slowing of the spaceship's middle clock by comparing it with two different clocks at different locations at rest in the spaceport frame. The spaceship crew saw slowing of the spaceport manager's clock by comparing it with two different clocks at different locations at rest in the spaceship frame. When observers in the spaceport frame observe the slowing of a spaceship clock, and observers in the spaceship frame observe the slowing of a spaceport clock, they are making clock readings at different space-time points. And as a result, they are measuring different things. Okay, so let's give a quick recap of what we've just seen. We said at the beginning that two ships, moving relative to each other, would each think that the other's clock was running slow, and we asked if this was a contradiction. The answer is no. We've seen this in two ways. First, we said that when observers at rest in each frame see clocks at rest in the other frame running slow, the two sets of observers are taking clock readings at different space-time points. Second, when the spaceport observers watched a single spaceship clock as it passed by, they observed the slowing of the spaceship clock compared to their own. But when the spaceport manager compared the series of spaceship clocks passing directly in front of them to their own clock, they did the same set of comparisons that the spaceship crew would do to observe the slowing of the spaceport manager's clock. These two sets of observations made by the spaceport observers are not the same, so there is no contradiction.